A star exists that is so immense that were it to take the place of our Sun, its outer boundary would extend past Saturn's orbit. It would engulf all inner planets such as Mercury, Mars, Venus, Earth, and Jupiter, and even light, traveling at the universe's maximum speed, would require hours simply to traverse its expanse. This celestial body is genuine, quantifiable, and currently ablaze. Concealed by thick interstellar dust clouds, identified as Stephenson 218, this expiring red supergiant represents the most massive star ever found. Its immense size defies conventional understanding and stretches the boundaries of stellar physics, compelling us to reconsider the ultimate growth potential of a star before its eventual collapse. If you're prepared, please consider liking this video and subscribing. The subject we are about to delve into is not merely another star, but rather the most colossal one ever recognized by humankind. It is a celestial behemoth that defines the ultimate limit of stellar evolution. We shall commence. Throughout the majority of human history, this particular star remained unknown to us, not due to its unformed state, nor its extreme remoteness, but rather because it was concealed. Enshrouded by dense barriers of interstellar dust, its luminosity never made its way to human vision. Even the most advanced optical telescopes of the 20th century would have perceived only in void of darkness where this star blazes. The narrative of the most massive star identified commences not with its finding, but with its obscurity. To comprehend the prolonged invisibility of Stephenson 218, our attention must turn to one of the most concentrated and intricate areas within our galaxy. The Milky Way is far from a pristine, clear stellar disk. Instead, it is interwoven with vast nebulae of gas and dust, which are the vestiges of previous stellar demises and the fundamental components for subsequent star formation. These nebulae accumulate most densely in the galaxy's central zones, areas where stellar genesis has been particularly vigorous. For eons, from our vantage point on Earth, gazing towards the constellation, scutum means peering into the congested core of the Milky Way. When observed in non-visible wavelengths, this area seems abundant and luminous, teeming with innumerable stars. Yet that brilliance is misleading. It merely shows the galaxy's closest strata. Beyond these, immense multitudes of stars remain entirely concealed, veiled by such dense dust that visible light is absorbed and dispersed well before it can break free. For hundreds of years, this implied that some of the most extraordinary stars within our galaxy remained completely unknown to humanity. Cosmic dust comprises minute particles, including carbon-based compounds, silicates, and solidified molecules, generally comparable in size to the wavelength of visible light. Upon encountering these specks, visible light disperses effectively, much like sunshine within a thick mist. This phenomenon leads to extinction. Stars situated behind dust formations either look fainter, exhibit a redder hue, or disappear entirely. Stephenson 218 is located behind some of the most significant extinction in the Milky Way when viewed in visible light. It is essentially obliterated. Its luminosity diminishes by tens of millions of times. Even if it ranked among the galaxy's most brilliant stars, optical telescopes would nonetheless detect nothing. Consequently, its detection necessitated the advent of an alternative observational method. Infrared radiation exhibits distinct characteristics. Its wavelengths are extended, many times greater than those of visible light, enabling it to navigate through dust particles with significantly reduced dispersion. While visible light is obstructed, infrared light penetrates, revealing a universe that seems dark and vacant to optical instruments. What appears dark and empty through optical telescopes becomes densely populated and radiant in infrared. During the latter part of the 20th century, astronomers commenced a methodical charting of the Milky Way using infrared wavelengths. Initially, these investigations did not yield sharp images. Instead, they uncovered irregularities, exceptionally luminous infrared emitters grouped in areas where visible light displayed virtually nothing. A particular anomaly of this kind emerged in the vicinity of scutum. During 1990, the astronomer Charles Bruce Stephenson documented a concentrated collection of infrared luminous entities while conducting a survey of the galactic plane. Back then, the available technology precluded thorough examination. This aggregation was recorded, identified, and mostly put aside, merely one more record among countless others. The nature of the stars inhabiting that cluster remained unknown at that point. Many years afterward, advanced infrared detection systems started to distinguish individual stars within this grouping. The discovery was astonishing. This star cluster, presently identified as Stephenson 2, contained an exceptionally large quantity of red supergiants, which are stars already in the concluding phases of their existence. Locating even a handful of red supergiants together is uncommon. Discovering more than 20 in a single compact area, the red supergiants are colossal stars existing within a transient evolutionary phase. They experience rapid life cycles, consuming their fuel quickly and expanding as their internal composition transforms. This particular phase lasts for only a minuscule fraction of a star's total existence. Observing numerous stars in this particular phase simultaneously necessitates precise timing. Stephenson 2 represents exactly such a captured moment. This cluster extends across merely a few light years, yet it encompasses dozens of stars that were born together, evolved in unison, and are now perishing collectively. It functions as a stellar graveyard in slow motion. It is a region where colossal stars expand, shed their outer layers, and prepare for violent conclusions. Among these immense celestial bodies, one star immediately distinguished itself. It exhibited greater infrared brightness than all the other stars, possessing a lower temperature yet an overwhelmingly high luminosity. Its energy emission could not be accounted for by its mass alone. Something about its dimensions was fundamentally distinct. That particular star would eventually be designated Stephenson 218. Initially, astronomers showed reluctance. Extraordinary assertions necessitate extraordinary proof. Determining the dimensions of stars located tens of thousands of light-years away is notoriously challenging. Luminosity alone is insufficient. A smaller star in close proximity can appear more luminous than a massive star situated at a great distance. Without accurate distance determinations, its physical size remains uncertain. For years, Stephenson 218 lingered in scientific limbo, suspected of being enormous but not yet confirmed. The breakthrough emerged from a convergence of several technologies. Precise infrared photometry unveiled its temperature and luminosity. Spectroscopy confirmed its identity as a red supergiant. And crucially, enhanced distance estimates positioned the entire cluster approximately 20,000 light-years from Earth. When those various elements were combined, the computations became undeniable. This was not merely a large star, it represented something unprecedented. Even conservative estimations positioned its radius at more than 1,800 times that of the Sun. Other analyses pushed this figure beyond 2,000 solar radii. The existing uncertainty did not weaken the conclusion. Instead, it strengthened it. Regardless of how the figures were adjusted, the star consistently proved larger than every known competitor. Stephenson 218 had quietly claimed its preeminent position. What makes this discovery especially striking is the seemingly ordinary appearance of the star. In early data, there was no explosion, no sudden flare, nor any dramatic event announcing its presence. It had existed for millions of years without fanfare, concealed simply because we had not yet learned how to observe properly. This represents a recurring theme within astronomy. The cosmos does not alter itself to accommodate our understanding. Its presence becomes known solely as our instruments advance sufficiently to detect it. Each novel spectral band, radio, infrared, X-ray, gamma, has brought to light completely new categories of celestial bodies that had always been present, awaiting discovery. Stephenson 218 stands as a prime example of such a discovery. It compels us to grapple with true magnitude, not merely conceptual or abstract cosmic distances, but the actual physical dimensions, the maximum size a solitary star can attain before the laws of physics themselves impose a limit. This particular star defies conventional understanding. It gently shatters expectations. It was presumed to be a compact celestial body. Typically dense and intense, Stephenson 218, by contrast, is dispersed, distended, and delicate. Its outermost strata are so tenuously bound that even a slight impetus, by astronomical measures, can propel matter outwards into the cosmos. It resembles a colossal entity formed of mist, sustained by a precarious equilibrium destined to fail. Nevertheless, for this fleeting period in cosmic history, it endures. The stellar grouping encircling it offers valuable perspective. These celestial bodies originated concurrently from an identical nebula under comparable circumstances. Still, none have expanded to such an extraordinary extent. Stephenson 218 embodies the utmost boundary of what is conceivable. It possesses an ideal confluence of mass, age, and intrinsic physical properties that enabled its growth beyond any star we have previously observed. Its distinctiveness stems not from being fundamentally unique, but rather from its infrequent manifestation. This segment of the narrative does not focus on quantitative data, but rather on its prior non-detection. It concerns how the most massive star known to us stayed undetected for nearly the entirety of human existence, not owing to its immense distance, but because our observational capabilities were insufficient. The cosmos unveiled one of its most extraordinary creations, only once humankind developed the capacity to perceive beyond the spectrum of visible light. Once observed, its presence became undeniable. While identifying a star is one matter, substantiating its actual immense size presents a completely different challenge. When observed from distances spanning tens of thousands of light years, even the most colossal stars diminish to mere pinpricks of illumination. No optical instrument, regardless of its magnification power, can simply enlarge them to disclose a discernible boundary. Viewed from our planet, a star comparable in size to our Sun and one vast enough to engulf Saturn can seem identically minuscule, indistinct, and remote. This constituted the primary hurdle astronomers encountered concerning Stephenson 218. To ascertain the dimensions of such a distant entity, researchers are unable to depend on direct photographic evidence. Instead, they are compelled to infer the star's physical magnitude circuitously, employing its emitted light as a metric. This methodology bears less resemblance to capturing an image, and more to deciphering a complex enigma where each component inherently contains ambiguity, and every hypothesis requires rigorous validation against physical principles. The initial element of this conundrum is luminosity. The luminosity of a star, as perceived from Earth, indicates the quantity of energy reaching our observational instruments. However, brightness in isolation can be misleading. A nearby candle, for instance, might appear more brilliant than a distant lighthouse. To convert observed luminosity into actual physical dimensions, astronomers are required to ascertain both the star's remoteness and its surface temperature. Determining its distance is the initial step. The most dependable method for gauging stellar separation is parallax, which refers to the perceived displacement of a star's location relative to more remote background celestial bodies as our planet orbits the Sun. This displacement is minuscule, even for stars in relative proximity. It is less than the breadth of a human hair viewed from several kilometers away. In the case of stars situated thousands of light years away, this positional alteration becomes nearly imperceptible. Throughout a significant portion of astronomical history, parallax measurements were restricted to stars in our immediate vicinity. Any object located deep within the galaxy was subject to considerable imprecision. This situation was transformed following the deployment of the Gaia space probe. Gaia meticulously recorded the coordinates of approximately 2 billion stars with unparalleled accuracy on multiple occasions. By discerning shifts as minute as microarc seconds for Stephenson 218 and its surrounding star cluster, Gaia ultimately established a trustworthy distance benchmark. Far from being unusually near, the star was genuinely distant, situated profoundly within the Milky Way's central areas. With its distance now fixed, its apparent brightness could be transformed into its true luminosity, the total energy it truly radiates. The figures were astonishingly high. Stephenson 218 radiates energy at a rate hundreds of thousands of times greater than that of our Sun. However, luminosity on its own fails to indicate a star's dimensions. A star's immense brightness can stem from either its extremely high temperature or its considerable physical extent. The subsequent crucial factor is temperature. Stellar temperatures are ascertained by astronomers through the examination of a star's spectrum, which illustrates how its light disperses across various wavelengths. Stars with high temperatures emit most intensely in blue or ultraviolet light, whereas cooler stars radiate in red and infrared. Stephenson 218's spectral analysis distinctly identified it as a red supergiant, possessing surface temperatures ranging from approximately 3,000 to 3,500 Kelvin. Such a temperature is considered low by astronomical measures, falling below that of our Sun and numerous stars observable without aid. This is precisely where the challenge of scale becomes inescapable. Should a star possess a comparatively low temperature yet release immense quantities of energy, its surface area provides the sole explanation. The star's immense size is a certainty. No alternative is permitted by the laws of physics. This correlation is dictated by a foundational principle known as the Stephenson-Boltzmann law. This law posits that the aggregate energy emitted by a star, its magnitude, is contingent upon two factors: its thermal intensity and its total surface extent. While temperature holds significant importance, the surface area is equally critical. Stephenson 218 emits a lower amount of energy per square meter compared to the Sun. However, its total surface area encompasses billions of times more square meters. Upon integrating the distance, luminosity, and temperature data, astronomers arrived at a conclusion that astonished even experts familiar with extraordinary scales. The computed radius surpassed 2,000 times the Sun's. To offer a sense of scale, imagine the Sun as a basketball. Stephenson 218 would then manifest as a sphere exceeding the height of a skyscraper. Nevertheless, even this particular computation was accompanied by a caveat. Red supergiants do not constitute solid entities possessing distinct boundaries. Instead, their atmospheres progressively dissipate into the vacuum of space. A definitive solid surface marking the star's termination simply does not exist. Astronomers are compelled to establish a demarcation, typically the photosphere, which is the stratum where the star achieves sufficient opacity for light to freely emanate. Within red supergiants, this demarcation resembles fog more closely than a solid barrier. This factor introduces an element of imprecision, contingent upon the specific wavelength, observational technique, and atmospheric model employed. The observable radius is capable of fluctuating by hundreds of solar radii. Certain measurements position Stephenson 218 nearer to 1,800 solar radii, while others extend beyond 2,300. Yet the pivotal insight remains. Every trustworthy measurement ranks it as larger than all other known stars, even when accounting for uncertainty in a cautious manner. Stephenson 218 continues to hold the title of the largest. An additional layer of complexity arises from its inherent variability. Red supergiants exhibit pulsation. Their expansion and contraction cycles span durations of several years. Their luminosity fluctuates, their atmospheric layers alternately expand and recede. Stephenson 218's size likely fluctuates by hundreds of millions of kilometers, meaning a measurement captured at one point in its cycle won't correspond to one taken years afterward. Such temporal variations by themselves generate margins of error exceeding the span of whole planetary systems. Nevertheless, even with this pulsation and these ambiguities, the star invariably ranks as the largest in all size comparisons. To directly determine a star's dimensions, astronomers additionally employ angular diameter measurements. This method quantifies the apparent size of the star in the sky, represented as an angle. Interferometers, which are arrays of telescopes distributed across vast distances, enable direct resolution of stellar disks for stars in close proximity. However, Stephenson 218 is too far away and too veiled for its angular size to be directly resolved. Nonetheless, astronomers can indirectly deduce its angular size from infrared flux distributions by utilizing models calibrated with nearby red supergiants. Once more, various approaches yield consistent results. All paths point to the identical finding. This isn't merely a slight record, nor is it a chance statistical anomaly. Stephenson 218's greater size isn't just by a small percentage, it surpasses others by hundreds of solar radii. Its confirmation wasn't delivered through one grand, sudden declaration. Instead, it gradually became apparent through numerous investigations as observational data became more precise and ambiguities diminished. Each study lent support to the next. Separate research groups arrived at comparable findings despite employing distinct initial premises. Such agreement is paramount in scientific inquiry. Had a single investigation asserted such an extraordinary measurement, its validity would have been challenged. As numerous independent analyses concur, certainty increases. By the late 2000s, the astronomical community had mostly embraced the implications of the data. The biggest star yet discovered was now known. What renders this especially noteworthy is Stephenson 2-18's apparent proximity to established theoretical boundaries. The principles of stellar physics dictate that stars cannot expand indefinitely. With stellar expansion, surface gravity diminishes, leading to greater mass loss as stellar winds remove matter. Ultimately, this growth ought to cease. Stephenson 2-18 is positioned precisely at that threshold. Its immense size means its outermost strata are only tenuously held by gravity. Consequently, matter is constantly escaping. The star is actively expelling its own substance into the cosmos, diminishing in mass even as it radiates light. This implies we are observing it during a brief period close to its peak expansion, just prior to its internal structure becoming unsustainable. These measurements go beyond merely identifying a record breaker. They serve to validate theoretical frameworks. Stellar evolution models need to account for not only the formation of such a star, but also its ability to persist long enough for observation. Each characteristic, including mass, metallicity, rotation, convection, and mass loss, must be precisely configured. Stephenson 2-18 represents more than simply the largest star known to us. It demonstrates the universe's capacity to propel stars to the absolute edge of physical viability, sustaining them there for a short duration before gravitational forces regain dominance. Ascertaining this reality demanded perseverance, accuracy, and many decades of advancements in technology. This necessitated developing methods to penetrate cosmic dust for galactic distance measurements and placing faith in equations validated by innumerable other stars. Once these measurements were complete, the outcome was indisputable. Within the Milky Way, there resides a star with a diameter spanning billions of kilometers. Its atmosphere possesses the capacity to engulf entire planets, and its immense scale defies all prior assumptions regarding the maximum possible size for a star. Now that its dimensions have been quantified, the fundamental inquiry arises: how can such a star possibly come into being? Initially, Stephenson 2-18's presence appears to defy logic. The universal law dictates that gravity draws all matter inward. As an object's mass increases, its gravitational attraction ought to intensify. Intuitively, we anticipate that the biggest stars would also be the most concentrated, compact, and tightly held together. Stephenson 2-18 entirely contradicts this assumption. Its immense size stems not from being densely packed, but rather from being largely devoid of matter. This star doesn't resemble a solid body. Instead, its construction is akin to a mist. To comprehend how such a colossal entity can persist without succumbing to its own mass, we must discard conventional notions of structure and embrace those specific to stars. Stephenson 2-18 isn't a homogeneous entity. Rather, it's a complex stratification of layers, each exhibiting distinct behaviors and functioning under varied physical conditions. The core is situated at its very center. This region constitutes a minuscule portion of the star's overall volume. Within this core, nuclear fusion takes place, a process where tremendous pressure and heat compel atomic nuclei to merge, thereby liberating energy. In contrast with the remainder of the star, the core is dense, compact, and turbulent. Nevertheless, even this central region of a red supergiant is smaller than Mercury's orbital path. Beyond that central region, everything expands. The core is enveloped by layers, where diverse nuclear reactions unfold. Hydrogen fuses in one layer, helium in another, and even heavier elements are found fusing further inward. Every shell generates power, and this energy is compelled to migrate outward. In doing so, it alters the star's form. A more pronounced decrease in density occurs the greater the distance from the center. In stars akin to our Sun, this reduction is progressive. Yet in red supergiants, it is profound. The outer layers swell outwards, distributing mass across immense volumes until gravitational force can scarcely retain them. The outcome is a star where the majority of its mass is situated predominantly centrally, while most of its volume remains largely vacant. Should one somehow calculate the average density of Stephenson 218 across its full diameter, the figure would be astounding. Indeed, its mean density is millions of times less than Earth's atmospheric density. A significant portion of its external shell possesses a lower density than the vacuum encountered by orbiting spacecraft. Consequently, size by itself can be deceptive. It is insufficiently massive to collapse inward under its own weight. The gravitational pull at its surface is feeble, to such an extent that a person might, in theory, float near its outer layers without being strongly drawn downwards, were the intense heat not immediately lethal. The pertinent query is what sustains the star's expansion. The solution lies in the movement of energy. Within the star's depths, nuclear reactions produce immense power. This energy propagates externally, pushing against gravitational forces. In the interior zones, energy is conveyed by radiation, with photons rebounding incessantly among particles, gradually spreading externally. However, further from the center, radiation proves ineffective. The matter there is excessively opaque. The thermal gradient grows excessively sharp. At that juncture, the star starts to churn. Convective processes assume dominance. Massive pockets of heated gas ascend toward the surface, cool, and then descend again, with fresh ascending matter taking their place. This phenomenon is common in boiling water, yet within Stephenson 218, its magnitude is unfathomable. Separate convection cells are capable of spanning distances greater than Jupiter's orbit. Complete planetary systems might exist within a solitary rising plume of gas. These convective movements are what enable the star to expand to such an extent. Convection efficiently moves energy, preventing the outer layers from collapsing while permitting them to stay cool. Lower temperatures result in less radiation pressure at the surface, which in turn permits the envelope to stretch outward without being immediately dispersed. This creates a paradoxical situation. The star is enormous due to its coolness. Its luminosity is a direct result of its enormous size. Every square meter of its surface releases less energy than the sun's surface, yet it possesses billions upon billions more square meters. The outcome is a star that radiates with the power of hundreds of thousands of suns, glowing a deep, subdued red. The star's outer atmosphere is not smooth. Instead, it is turbulent, uneven, and perpetually changing. Bright regions indicate where hot material rises, and darker regions denote sinking gas. The surface slowly churns, reshaping itself over periods of months and years. Moreover, there is no sharp boundary, which differs from a planet. A red supergiant lacks a clearly defined surface. Its atmosphere progressively thins, gradually transitioning from dense gas to tenuous plasma and then to a near vacuum. Astronomers define the surface as the photosphere, which is the layer where light can finally escape unimpeded. Yet above that lies an extended atmosphere, stretching millions of kilometers farther out. For Stephenson 218, that extended atmosphere is so vast that defining where the star truly concludes becomes partly a matter of convention, depending on wavelength and method. The apparent size can fluctuate. This is one reason why size estimates vary. Even when accounting for this ambiguity, the star remains unparalleled. The fragility of this structure is impossible to overstate. The outer layers are only loosely bound. Minor disturbances, pulsations, convection, and radiation pressure can entirely lift material away from the star. Stephenson 218 is actively losing mass, shedding its external layers into space through powerful stellar winds. This mass loss is not gentle, it is unceasing and vast. The star sheds more mass in a single year than the sun will lose over millions of years. Dust forms in the cooling outer layers, absorbs starlight, and is propelled outward by radiation pressure. Dragging gas along with it over time, this process will erode the star's envelope. This is the reason why such extreme size cannot endure. Stephenson 218 is close to the upper limit of what stellar physics permits. Any further expansion would sufficiently weaken surface gravity that the star would simply tear itself apart. The balance it maintains is temporary, delicate, and unstable, and that instability is the crucial factor. Red supergiants represent a brief evolutionary phase. They are not the natural endpoint of stellar life, but rather a transitional state, a swelling before collapse. The very processes that inflate the star also signal that its internal structure is rapidly changing deep inside. Heavier elements are forming. Each stage brings the core closer to a point where fusion can no longer provide support. When that moment arrives, the core will collapse, and the vast envelope will no longer be sustained from below. Its immense dimensions will prove to be its weakness. Once the collapse initiates, it will proceed rapidly, outpacing the reaction time of its external strata. The subsequent shockwave will tear through the fragile outer shell, encountering minimal opposition. A celestial body that once stretched for billions of kilometers will be scattered throughout the cosmos within mere hours. However, at present, its configuration remains stable. Stephenson. 218 represents one of the most extraordinary material formations the cosmos is capable of creating. This star is formed not by solid mass, but by equilibrium. Its immense luminous atmosphere is sustained by energy emanating from its central core. Though it is smaller than numerous planetary paths, this is not a permanent structure. Rather, it is a fleeting instant. It's a temporary physical configuration, enabling a star to expand beyond any other we have observed. Poised on the brink of disintegration, it gradually disassembles even while radiating light. This realization reveals that its composition provides an answer to a more profound inquiry. The universe's most massive star isn't mighty due to its robustness. Instead, its power stems from its delicate nature. Stars such as Stephenson don't originate as colossal entities. Their existence commences with intense, yet dense, scorching, blue, and intensely luminous characteristics. Far prior to this star expanding into the most immense known entity of its type, it was a colossal blue star. It consumed hydrogen at a pace that vastly overshadows anything our sun will ever undergo. To comprehend how it attained its present swollen condition, we must trace its existence from its inception, as the destiny of massive stars is determined at their birth. Everything originates with mass. Stars come into being when immense gaseous nebulae succumb to gravitational collapse. The majority of that gas never integrates into the star. Instead, radiation and stellar outflows propel it away as the nascent star flares to life. Merely a small portion persists. This remnant dictates the star's complete trajectory. For Stephenson 218, its original mass was exceptional. It probably ranged from 25 to 40 times the solar mass. That quantity alone determined its fate. Colossal stars have short lifespans. Whereas our sun will steadily combust for 10 billion years, a star possessing dozens of solar masses depletes its energy reserves within a mere few million years. The cause isn't a lack of resources, but rather an abundance. Increased mass results in more potent gravity, which in turn compresses the core to incredibly high temperatures. At such temperatures, nuclear processes intensify significantly. The core of Stephenson 218 formerly fused hydrogen at temperatures reaching tens of millions of degrees, predominantly via the carbon-nitrogen-oxygen cycle. This particular fusion mechanism, being considerably more susceptible to temperature changes than the one energizing our sun, leads to an astonishing energy release and devastating fuel depletion. From the instant it flared into existence, the star had a rapid life. In this initial period, it bore no resemblance to the red giant observed currently. It possessed a smaller stature, possibly just a few dozen times the sun's radius, yet it was intensely hot, emitting blue and white light and saturating its environment with ultraviolet rays. Any planets in its vicinity would have been immediately rendered sterile. Over millions of years, the star preserved a fragile equilibrium. Gravitational forces exerted an inward pull, while nuclear fusion generated an outward thrust. This stability persisted as long as hydrogen combusted within the core, but hydrogen is not an eternal fuel. With fusion transforming hydrogen into helium, the core gradually accumulated inert byproducts. Helium does not undergo fusion with the same facility. When the core's hydrogen supply was depleted, the equilibrium failed, lacking fusion to oppose gravity. The core then compressed. In doing so, it grew hotter, initiating the burning of hydrogen in a layer encircling the core. This marked the critical juncture. The combustion within the shell emits a greater amount of energy than core fusion, and that energy must be dissipated. The star's sole response was to expand its external layers, which swelled outwards. Over millennia, these layers cooled as they dispersed, causing the formerly dense blue star to evolve into a red supergiant. This enlargement wasn't gradual. Rather, it was a slow-motion explosion. The star's radius grew by hundreds of millions of kilometers. Surface temperatures decreased, and the star turned red. With its expansion, the surface gravity diminished, facilitating the escape of matter. In the case of stars like Stephenson 2D18, this stage can attain immense scales. More massive stars shed their external layers too rapidly to achieve such extensive expansion. Conversely, less massive stars never produce sufficient energy to swell to these dimensions. A star exists within a confined range where its expansion and the retention of its material are in perfect equilibrium. This equilibrium enabled it to become larger than any other known star. With the star's ongoing evolution, fusion processes progressed both internally and externally at the same time. Helium commenced burning within the core, generating carbon and oxygen. Hydrogen persisted in burning in the layers situated above it. Every subsequent fusion phase modified the star's inner composition, boosting its energy production and fostering greater instability. Nevertheless, from an external perspective, the star seemed almost tranquil, a massive red luminescence gently throbbing, releasing material into the cosmos. This apparent serenity is misleading. The red supergiant stage isn't an extended period of rest. It represents the concluding chapter. It endures for possibly a few 100,000 years, or even less when viewed cosmically. This is a brief interlude preceding disaster. Stephenson 218 is presently experiencing this temporary halt. Its colossal dimension doesn't indicate steadfastness, but rather impending transformation. Each stratum of the star demonstrates that its core is exhausting its possibilities. Fusion processes now advance using heavier elements, with each subsequent phase being briefer than the preceding one. What consumed millions of years during the star's early existence now requires thousands or even just centuries. The star is consuming its residual fuel at an increasing rate, and consequently mass depletion amplifies potent stellar winds. These winds remove matter from the external shell. Pulsations transmit shock waves throughout the atmosphere, expelling gas and dust into the void. The star is literally disintegrating at its periphery, even while its core becomes more compressed and hotter. This material depletion is significant. It dictates the star's eventual demise. Should sufficient matter be expelled, the core might collapse into a neutron star. Conversely, if an excessive amount of mass persists, it could give rise to a black hole. Stephenson 218 is situated close to that demarcation. Its ultimate destiny remains unclear, yet one outcome is unavoidable. The core will ultimately arrive at a state where fusion is incapable of generating energy. Once iron develops in its center, the star's nuclear reactor will cease operation. Gravity will triumph instantaneously. The core will undergo collapse, and the immense outer layer, comprising all that renders the star so gigantic, will be ripped asunder in a supernova blast. The biggest known star is observable solely because we are witnessing it at precisely the opportune time. Several 100,000 years prior, it possessed a smaller size. Several 100,000 years hence, it will have vanished. This is precisely what renders Stephenson 218 exceptional. Beyond its sheer magnitude, its timing is crucial. We are observing the zenith of its stellar growth. This fleeting physical configuration yields an object of such vastness that it verges on the inconceivable. Stephenson 218's colossal dimensions do not signify a long lifespan, rather they serve as an omen. Stars do not swell to such proportions when they are in good condition. Their expansion occurs because their existence is nearing its end. The distended crimson envelope, which renders this star the largest known of its type, is the outward manifestation of a core on the verge of implosion. Within the depths of Stephenson 218, concealed by its immense diffuse outer layer, the star is rapidly undergoing the ultimate phases of nuclear fusion. These reactions remain unobservable, yet they govern all subsequent occurrences. Within typical stellar bodies such as our Sun, fusion unfolds gradually and consistently, transforming hydrogen to helium over eons. Conversely, in massive stars, fusion constitutes a frenzied rush. Following the depletion of hydrogen and helium at the core, fusion progresses to successively denser elements. Carbon converts to neon, neon to oxygen, and oxygen to silicon. Every subsequent phase generates diminished usable power and persists for a significantly reduced duration. The star is depleting its residual propellant at an ever-increasing rate. This process forms an internal structure composed of layers, frequently likened to an onion. Distinct elements are fused within each concentric layer, while the core becomes increasingly compact and thermal. However, this progression encounters an absolute boundary. Iron marks the terminus of the nuclear pathway. The fusion of iron fails to liberate energy. Instead, it absorbs it. Once iron gathers in the central region, the star forfeits its ultimate means of sustenance. Consequently, the central mass implodes. The implosion is abrupt and forceful. Within a mere fraction of a second, Stephenson 218's core will implode at a considerable proportion of the speed of light. Matter is compacted to inconceivable levels of density. Protons and electrons are forced into combination, resulting in the creation of neutrons and emitting a torrent of particles with negligible mass known as neutrinos. This eruption of neutrinos transports a greater amount of energy within moments than the star has radiated as luminosity over the full duration of its existence. The imploding core fails to merely vanish. Upon attaining nuclear compactness, the inward progression ceases suddenly. The core becomes rigid, springs back, and propagates an outward-moving shockwave. This shockwave marks the genesis of a supernova event. Given the magnitude of such a star, the shockwave initially encounters minimal opposition. Stephenson 218's outer layer is immense, yet attenuated, resembling a diffuse cloud rather than a solid formation. The shock will propel itself externally, tearing across a gaseous expanse spanning billions of kilometers. Several hours following the onset of the implosion, the shock will arrive at the exterior. At that point, the star will momentarily transform into one of the most luminous entities in the galaxy. From Earth, at a distance of 20 millennia of light travel, the explosion could nonetheless be observed, notwithstanding the dense cosmic dust presently concealing the star. The blast will warm adjacent dust particles, leading them to radiate powerfully in the infrared spectrum. Over a span of days or weeks, a solitary expiring star could surpass the luminosity of billions of other stars collectively. This phenomenon represents the scaling paradox. The most massive star identified will conclude its existence in an occurrence that condenses its ultimate destiny into mere instants. The nature of the remnant at its core is contingent upon the quantity of mass remaining post-detonation. Should sufficient matter be expelled, the core will stabilize as a neutron star. This city-sized entity holds more mass than the Sun, rotates swiftly, and emits radiation beams that can be detected across the galaxy. Conversely, if an excessive amount of mass persists, gravitational forces will overcome even the pressure from neutrons, causing the core to collapse into a black hole. Stephenson 218 is positioned close to this critical boundary. The substantial loss of its mass over an extended period might sufficiently diminish the core to create a neutron star, or it could still undergo collapse into a black hole. While it silently anchors the expanding cloud of remnants, scientists are currently unable to forecast which result will materialize. One certainty is that the detonation will bring about a profound transformation. The star's external strata will be propelled into the cosmos at speeds reaching thousands of kilometers per second. Dense elements, synthesized within the star's core and during the explosive event itself, will disperse throughout the adjacent area. Substances like carbon, oxygen, silicon, calcium, and iron, all crucial for the formation of planets and the emergence of life, will be disseminated across the galaxy. This colossal star will be converted into fundamental building blocks. Across millennia, the expanding remnants will decelerate, cool down, and intermingle with the gas found between stars. Impact waves will compact adjacent clouds, potentially initiating the genesis of new stars. The demise of one stellar body will sow the seeds for the emergence of others. This mechanism illustrates the universe's self-renewal process. The detonation of Stephenson 218 poses no danger to Earth. Its immense distance and significant obscuration prevent any threat. However, its significance will be more profound, as it will play a role in the continuous chemical development within the Milky Way, thereby enriching subsequent generations of stars and planetary systems. A concluding element of uncertainty heightens the dramatic aspect, given that light requires time for its journey. The stellar body we perceive currently does not represent its present-day existence. Instead, our observation reveals it as it appeared 200 centuries in the past. The implosion might have already taken place, with the supernova's shockwave potentially already expanding outwards. The light particles conveying information about that demise could already be in transit, still traversing the immense interstellar voids. Alternatively, the star could endure for an additional 100 millennia, gradually shedding its outer layers. Radiating a red glow in the darkness, its true status remains unknown to us. The most massive star identified exists veiled by both temporal distance and cosmic dust. Its current condition is concealed due to the limited velocity of light. We perceive its history and, without realizing it, anticipate the arrival of its future. Stephenson 218's presence represents more than mere intrigue. It serves as a demarcation point within a cosmos dictated by physical principles. No entity possesses genuinely boundless characteristics. Mountains ascend to a finite elevation before gravitational forces cause their descent. Oceanic depths extend only to a certain point before immense pressure alters the composition of matter. Stars similarly face limitations. Their growth can be substantial, yet it is not without bounds. Stephenson 218 seems to reside exceptionally close to that maximum, inhabiting the outermost boundary of what stellar physics allows. This particular star compels us to confront an unsettling query. Does it represent the absolute largest star in existence, or merely the most massive one we have identified to date? The Milky Way galaxy encompasses hundreds of billions of stellar bodies. Numerous others are obscured by cosmic dust, far denser than the nebulae that concealed Stephenson 218. Throughout the majority of human history and even presently, we have accurately determined the dimensions of only a minuscule proportion of red supergiants with sufficient exactitude to establish their relative sizes. The current record-holding star might not, in fact, be the ultimate champion. It could simply be the initial one we managed to observe distinctly, yet compelling arguments exist to suggest this star approaches the genuine physical boundary. Models of stellar evolution indicate that stars are incapable of expanding without end. With the expansion of a red supergiant, its gravitational pull at the surface diminishes, and the rate of mass expulsion increases. Stellar winds strip away the external strata at a pace exceeding the rate at which expansion can contribute to them. Ultimately, a star attains its largest possible dimension when its expansion and material loss reach equilibrium. After this, additional growth is no longer feasible. Stephenson 218 seems to be precisely at this point of equilibrium. The star's external atmosphere is so tenuously held that it continuously expels matter into the cosmos. Its continued existence is not due to a fixed configuration, but rather a transient equilibrium between the outward push of energy and the inward pull of gravity. Such an equilibrium is unsustainable over vast cosmic durations. Consequently, the most massive stars are not necessarily the largest. Stellar bodies possessing initial masses significantly exceeding that of Stephenson 218 follow a distinct evolutionary path. Their powerful emissions remove their external strata before any significant expansion can occur, resulting in dense, intensely hot entities referred to as Wolf-Rayet stars. These stellar bodies are potent yet diminutive. They never attain giant proportions. The most colossal stars emerge only within a restricted spectrum of initial mass. They possess sufficient mass to produce immense energy, yet not so much that their outer shells are shed too rapidly. This particular star seems to represent an almost flawless illustration of that equilibrium. Should more colossal stars exist, they are probably uncommon, ephemeral, and well concealed. Advanced telescopes in the future might eventually locate them. Modern infrared observatories are commencing to penetrate further into the galaxy's dust-laden sectors. Every enhancement in detection capability increases the cosmic volume accessible to our exploration, extending beyond our present limitations. Perhaps another, even larger and more extreme giant star is burning, awaiting its revelation. Alternatively, Stephenson might indeed be unparalleled. Both potential results carry significance. Should it continue to be recognized as the most massive star, this indicates that the principles of stellar physics impose a definitive upper limit on size. Should its record be broken, it would reveal the universe's capacity to extend those boundaries even beyond our current comprehension. However, a more profound meaning exists beyond mere statistics and classifications. This celestial body serves as a reminder that the cosmos does not expand proportionally. It transitions abruptly from the understandable to the unfathomable without prior indication. Our sun, which governs our heavens, is quite humble on a universal scale. Complete planetary configurations could reside within the gaseous envelopes of stars invisible to our naked eye, yet their existence is confirmed. Photons emanating from Stephenson 218 departed its exterior 20,000 years prior, well in advance of contemporary civilization and recorded history as we understand it. These light particles traversed the vast expanse of the galaxy. They navigated through cosmic dust until arriving at devices constructed by a species that developed on a minor terrestrial world orbiting an average star. This interrelation is crucial. The constituent atoms of Earth were forged within primordial stars. The iron within your bloodstream, the calcium comprising your skeletal structure, and the oxygen you inhale were all generated inside stars akin to this one. They were subsequently dispersed by cataclysmic events similar to the one destined for it. Fundamentally, Stephenson 218 is not remote. It is intrinsically connected to us. The most colossal star identified is not merely a symbol of immense scale. Rather, it serves as an emblem of ongoing processes, of cosmic cycles, illustrating the perpetual movement of material from stellar bodies into the void and its eventual return. It contributes to the formation of planets, the emergence of life, and the development of sentient beings able to reflect and comprehend. Eventually, Stephenson 218 will disappear in a supernova explosion, leaving a dense core within an expanding nebula of enriched elements. Astronomers of tomorrow will examine that residual object and piece together the nature of the star that formerly occupied that space. While its distinction might be surpassed and its designation forgotten, the insights it provided will endure. The cosmos permits stars to attain astounding dimensions, though not indefinitely. It enables them to radiate with the luminosity of hundreds of thousands of solar bodies, yet only for a limited duration. Furthermore, it grants diminutive observers, circling a humble star, the capacity to unveil these realities through perseverance, mathematical analysis, and photons that have journeyed for millennia. The most colossal star currently identified shines this evening, concealed from direct human sight, yet brought to light through intellectual comprehension. Through its discovery, we come to understand not only the vastness of the cosmos, but also the boundless nature of human curiosity. Should you enjoy this video, please remember to hit the like button and subscribe. It has a substantial impact and assists the channel in its development.